Good day, students, and I welcome you to the online version of Numerical Analysis 363. And I believe you've enjoyed your weekends wherever you happen to find yourself. And it's time to get back to class. So for numerical analysis, we've started with the introduction to numerical analysis, where we got to see how to approach problems in the industry and how to solve it. We also further dive down to see how we get to use computers and machines to generate some of our solutions. And with that, we progress to error analysis, where we started playing with accuracy and that of precision. We took a look at that. So we've gone through all these areas, and now we are currently at the chapter 2, where the objective was to understand the distinction between accuracy and precision. Also get to see how we get to quantify these errors that we are going to accumulate once we are in the domain of numerical analysis, understand the term roundoff errors and how they do occur in digital computers because they have limited ability once it comes to representing numbers. So we saw an example in the case of the pi, where we show the first 1,000 decades of pi, and we also saw that our calculators, our mobile phone, smart devices were not able to give us up to that level of precision. So we are going to also talk about that. And we are also going to look at understanding why floating point, that is decimal places, have limits on their range and precision. And we are going to also talk about truncation errors and when exact mathematical formulations are being represented by approximations such as that is where we usually experience truncation errors. And we're also going to demonstrate what we call the finite differencing scheme based on the Taylor series. We're just going to do that. And above all these, we are going to look at how to minimize these errors. So we started the lecture with you being engineers, you are going to constantly find yourself having to accomplish some tasks based on some uncertain information. And uncertain information here, I'm referring to some errors that you are going to, let's say, see once you're on the field. And with all that, we need to find ways of accounting for all these errors. So we started off with accuracy and precision, where we got to see the difference between accuracy and precision. And now let's see how we can really quantify these two stuff. Now, you should know that throughout this lecture material, the term error will be used to represent both accuracy and precision, but you should know like the difference between these two. But in terms of this lecture material, we are going to use the term error to generalize this precision and accuracy. Now, for us to do so, just as we saw in the example when a student was to measure a gold bar and that of the bridge, we could see that they were both making an error of 1 centimeter each. Now, we need to find a way of quantifying these errors, just as we said in our objective. And from what we've seen so far, it could be observed that for us to have our true value, this true value will be an addition from the approximated value and that error. Once we combine these two, we are definitely to get our true value that we seek. So rearranging this to make the error term the subject here is of no doubt that our error will always be equal to the true value and that of our approximated value. Okay, so basically this is how the general form to estimate any form of error. So just as in the case of the bridge and the gold bar, we estimated the error based on the true value minus the approximated value. So just in the case of the gold bar where we had the true value to be 10 centimeters and that of our approximated, the one that our student measured and got 9 centimeters. So the 10 minus the 9, we had an error of 1 centimeter, and we used this formula in calculating that. However, we also observed that if we are to look at it from this point, yes, they are both making an error of 1 centimeter each. But if you are to look at it like from a more technical point of view, these errors are not the same. And for us to denote that, we go by the term relative error. That is where we try to estimate the error based on certain circumstances in which we find ourselves in. So with this same error that we see in this equation could be modified into a relative form, which we have here. So in this case, all that we do is to try to determine the error and divide it by the true value. Okay, so the whole of this thing up here gives us the error, that is the true value, minus the approximated value all over the true value again, and that gives us relative error. Now, because we are in the field of engineering where the dynamics of the job might change and modify itself from time to time, we are going to make use of this relative error a lot. Okay, and if you would like to really express this relative error, we will have to multiply this relative error by 100 so that we could really quantify our error in terms of percentages. So if you are to look at this, let's try to look at this from the example that we had. That is when these students or graduates are being given the task to measure the bridge and that of the gold bar. Now, relatively, the first student is making an error. The one calculating the bridge will make somewhere 0.001 error. That is relative error if we are to look at this formula here. Okay, but however, if we are to express this in terms of percentages, he's going to make an error of 0.01%. Okay, in that same case, the one in the case of the gold bar is going to make a relative error of 0.1, but in terms of percentages, he's making an error of 10%. Okay, so the relative and the relative percentage error is just multiplication or just multiplying the relative error by 100% or 100 so that we could represent the error in terms of percentages, and that is exactly as we are having here. Okay, so that is how we are going to really measure that in terms of numerical analysis. We would always prefer to see the relative error, that is in terms of percentage, and we are just going to look at that. So in this case, that is how we are going to look at it almost all the time. Now, if you look at something from the previous expression that we have here, now you can see that we have an error expressed in terms of t. This t is the one that I'm talking about. So with this, anytime you see error of t, it means that we are basing on the true value to estimate the approximated value. Okay, so the error is being obtained from the true value minus the approximated value. Please forget of this true here. Okay, just copy and paste. So it's just approximated value all on the true value. Okay, so anytime we have this case, we always base on the true value, we subtract it from the approximation all over the true value. So anytime we are estimating our errors based on the true value, we always like to represent this error by this error of t. However, when you come to the field of, let's say, engineering and science, or let's say when you come to the field, the true value is rarely known, in the sense that if you already know the true value, why do we have to move on, or let's say worry ourselves in determining an approximate value? So because this true value is really not known in the industry, the idea here will be to approximate the error based on a normalized form of this error. That is to use the best available estimate of the true value. And that is what we are going to use as the present approximation. So in place of the true value, we are going to use a normalized form of this true value, which we have to be the present approximation. So with all of our errors in here, we are going to make use of a certain present approximation minus a previous approximation all over this present approximation. So once we are able to get this, we can estimate this normalized error. And remember that with everything, we are going to determine in terms of percentage. So we always multiply by 100%. Okay. Now, because this time we are not going with the true value, but rather an approximation of the true value, our error here will be denoted by error alpha, more or less like an approximation, for the alpha referring to an approximation. So if you look at the first one where we use error t, we are determining the error based on a true value as we see in here. So error is equal to true value, okay, but this is the case we don't know the true value, so we try to use the present approximation minus the previous approximation all over the present approximation, and that is going to give us an error alpha for the error from the approximation. Okay, now let's watch something here. If you perform or you try to estimate this error, should I say about two things can occur here. One, if your previous approximation happens to be greater than the present approximation, it means that we are going to end up with a negative value for the error. In this same case, if your present approximation happens to be greater than your previous approximation, then we are going to get an error which is positive. Now, in numerical, we don't really dwell so much on this signs here. So for us to do away with that, we are just interested in the exact or the absolute value of the error. And for this case, we are going to find the absolute of all of our errors in most of these cases. So after estimating the error, that is this error A, most of the time we are going to find its absolute, okay? And that is what we have here. Now, how do we get to know whether the error that we have obtained is acceptable? This is going to be acceptable based on what we call the tolerance, a margin in which we are willing to accept, of which we are going to denote by the tolerance. Now, in practice, you as the engineer would have to base on some subjective, let's say, reasoning for you to come up with your tolerance. But in the case of the classroom, I would go with two approaches. There are certain cases that I would specify this tolerance. For instance, I can tell you to perform your computation repeatedly until you get to an error which is less than maybe 0.05%. Okay? In cases two, I might not give you this tolerance value. And once I don't give you this tolerance value, it means that you have to dwell on this formula to estimate your tolerance. Now, this tolerance, which is equal to 0.5 times 10 raised to the power 2 minus n, where this n will be the number of significant figures of which I would specify, okay? Remember that for consistency of all calculation, I would restrict you to some notations like the number of decimal places to use, among other things, okay? And once I do that, I'm also going to restrict you on this so that you all get the same answer. So once I specify the number of decimal places to be used, it means that it will give you a fair idea of this n value so that it could help you estimate your tolerance. Okay. So let's try to take an example here and see how to estimate the error. Okay. And with that, we are going to dwell on the Maclaurin series, which you guys were, I think, were taught in calculus, 150. So with this, the Maclaurin series has been expressed here, which is also an exponential function. So basically, this is what we are going to do here. For us to estimate this, we are going to take them term by term, okay? For instance, suppose that we like to estimate maybe e raised to the power 0.5. We are going to take the first term, that is ex is equal to 1, which is just equal to 1. We are just going to look at that. After that, we take ex is equal to 1 plus x. That we are taking the first two terms and do it gradually, and we see how the errors propagate as we move on forward. So in reality, you could see that even just without having to go through, you can have the idea that once you would like to estimate e raised to the power a certain number, the more terms that you include, the better your estimate to the true value becomes, okay? So with this, we are just going to try with one example. That is, we are going to estimate e raised to the power 0.5, where in this case, our x that we have here is just equal to this 0.5, okay? So we are just going to try to estimate this sequence and see how these errors are being generated as we move on. So we know just right from punching our calculator, we could see that exponent of 0.5 is equal to 1.648721, and this happens to be the true value. But mind you that we are always not interested, we don't usually see this true value in the field. But for now, let's see the true value and see how best our error tends to what diminish as we move on forward. So with this, we are going to estimate for exponent of 0.5, and we are going to repeat this until the absolute value of this approximate estimate falls below a certain specified criteria, which is the same as our tolerance, okay? But in this case, we are restricting ourselves to 3 significant figures. So if you remember from this formula that we had earlier, it means that if you like to estimate our tolerance, when are we going to stop? It means that we are going to calculate this expression based on n is equal to 3, because we are dealing with 3 significant figures right from this question, okay? So let's see how we generate this tolerance. Now, before we get to estimate our error, it means that first we have to know when to stop. And when to stop is being determined by the tolerance, okay? So with this, let's try to estimate the tolerance as we see right in here. So with this, we could see that our tolerance will be equal to, into bracket, 0.5 times 10 raised to the power 2 minus n. And remember that our n here was equal to 3. So that is why we have 2 minus 3. All times the percentage sign. And once we estimate this, we are getting 0.05%. So regarding to this question, it means that we are going to solve until our error is less than 0.05%. That is what is being given by the tolerance, okay? So now that we know our tolerance, let's move on to perform our first iteration. And remember that the Maclaurin series was giving us Ex is equal to 1 plus, I think the next one will be x, then plus, I think, s squared on 2, then it moves on to factorial kind of thing, then it moves on forward. So let's see, if we take the first term, which is up to this portion, and forget of the rest, it means that wherever, even if we put in x or something, we are still going to get 1, okay? So for the first iteration, that is when we consider only the first term, we are going to get our answer to be equal to 1, okay? Now let's see how we calculate our error from this first iteration. That is when Ex is equal to 1. So remember that the formula for estimating the error was the true value minus the approximated value, all on the true value. And with this, remember that our true value was equal to 1.648721 absolute higher. So that will be our true value minus our approximated, which we just estimated from the first iteration, all over 1.648721, all times 100. And with this first iteration, we are making an error of 39.3%. Okay, that is, if we are to estimate for the value of exponent of 0.5, it means that, and taking only the first term, it means that we are making an error of 39.3%. Okay, now this is for the ET, that is calculating the error based on the true value. Now, what if you want to estimate the error based on the approximated value, that is the error alpha? Now, remember that this error alpha is based on a present approximation minus a certain past approximation all over present approximation, all over a present approximation. But if you look at what we have in here, we do not currently have a present approximation, or we do have a present approximation, all right, but we do not have a past approximation. So for this first iteration, we cannot estimate our error based on the approximated value, but we could do this in the next iteration. So with the next iteration, that is when we take the first two terms of the Maclaurin series. And for the first two terms, that will be equal to EX, which is equal to 1 plus X. Remember, we are taking the first two terms now, okay? So for us to estimate our X is equal to 0.5 again, that is going to be 1 plus 0.5. And this 0.5 here is from this X that we are trying to estimate. So we just substitute our X into this formula and we get 1.5. Now with this, let's try to estimate our error. But first, let's look at the true error. And this, from the true error, remember that this is based on the true approximation minus the true value minus the approximation. And with this, once we do this, we are getting 9.02%. Okay. Now let's look at the approximated version of the error, and this is where we use the present approximation minus the past. And remember that with this, the present approximation, that is the one with iteration 2, we had our value to be equal to 1.5. And for the past approximation, we had 1. And this one was obtained from the first iteration. Okay. So the present will be the immediate approximation you just calculated, and the past will be like the former approximation you calculated. So that is why we are getting 1.5 and 1. So the present approximation minus the past approximation all over the present approximation. So this is how we get to estimate our error based on the approximations alone. Okay, so times 100, which would this time give us 33.3%. Now watch it, that because we've not yet gotten to our tolerance, which says that we should perform the iteration until we get to 0.05%, it means that we are not going to stop here. We are going to move on to the next term, and if we still do not achieve that criteria, it means that we are going to continue until we get there. Okay, so once we do that, we are going to estimate repeatedly until we get to a certain place where the error is going to give it something less than the tolerance. And remember that the tolerance was equal to 0.05. Okay, so if you look at from the first iteration where we had the result to be equal to 1, remember that we had the true value to be equal to 39.3. But at this particular point, because we do not have any past value, we could not estimate our error based on the approximation. Now we moved on to the iteration 2, and we had our solution to be 1.5. And with that, we had our true error to be 9.02 and our error based on the approximation to be equal to 33.3. Because this was still not less than 0.05, it means that we had to move on to the next iteration where we added the next term, making it 3 terms now. And once we do that, we had the result to be 0.625, of which we encountered an error of 1.44% based on the true approximation or the true value, and an approximated error of 7.69, which was still no less than our tolerance. So we move on adding term by term, but as soon as we got to the 6th iteration where we had 1.64897917, we had a true error of that, and we had an approximate error of 0.01. But because this happens to be lesser than our tolerance, it means that we've achieved that iteration, the requirement of which this error will be acceptable. So once we hit an error less than the 0.05, which is the tolerance, then we can successfully end our computation in this case. Okay. So anytime that you are performing numerical analysis and we would like to know when to stop, this is basically how we go through. Okay. So it's like two things here. It's either I give you the tolerance or I do not give you the tolerance. If I do not give you the tolerance, it means that you have to estimate that based on this formula that we have in here. Okay. So this formula can come in handy when I do not give you the tolerance value. Okay. But if I'm merciful enough to give you the tolerance value, then hooray. Okay. That is going to save you some headache and time from solving for that tolerance. Okay. So always remember that all that you need for this tolerance is to know your number of what significant places, which is the n. And once you know this n, you can really estimate this tolerance. Okay. So with this overview of how to estimate errors in that, let's see really where these errors comes from in terms of numerical errors. Now these errors, students will come from so many angles, and we did talk about some in class. Okay. But basically, let's look at some of the major sources. Okay. And the first one will be measurement error. Okay. And we are going to look at that. But before we look at this, we also demonstrated in class that even with all our devices that we are making use of, our calculators, our instruments at the lab, these instruments all come with some margin of precision. And once you buy this software or let's say device for the first time, it's likely to be within the manual stating specifically the margin of precision of those devices. Okay, so they all come in that form. So with the measurement error, which we've been talking about, once you have a device and you are measuring something, and because this device comes with some margin of precision, this measurement error is something that is really unavoidable because that is where the device can get up to. So once we are using that, we definitely encounter that error unless we go in for a supercomputer which will take off all of the digits for a specific number. But because we are not there yet, this sort of error is unavoidable to start with. Now let's look at the next one, that is the truncation error. And this happens whenever a series, or let's say a sequence or a series of computational steps necessary to produce an exact result is being truncated prematurely. So let's take a look at our Maclaurin series, which is a series through to infinity. Suppose that we could get all these series and place in the value of x. It means that we are going to get exactly the true solution. Okay. But whenever we try to take some terms off, that is when we try to truncate some of this sequence off, we are definitely going to come up with an error. And this kind of error is being termed as the truncation error. That is when we say truncate or terminate the series at a certain point prematurely, and that brings kind of error is termed as truncation error. We also have the rounding error, and this is normally seen like in the case of calculators. You punch in a value, but because of the number of precisions being specified, it will have to round off that number. So for instance, in the case of the value pi, it's going to round off, I think, at the sixth decimal place or something. So it's going to round off or either round down or round off. And these are two terms that we are going to look at very soon. Okay. So you get the idea of rounding off and rounding down numbers. We are going to look at that. We also have accumulation errors. That is when if you are to start calculation or let's say estimations right from the beginning, if you start let's say with an error and you are going to use this same estimate in other iterations, it means that right from the beginning you are accumulating errors until you get to the last point, which would let's say inflate that error that you have. Okay, so once you start accumulating error based on some analysis that you are doing, then that's could be termed as accumulating errors as you move on. Okay, so these are some of the sources of errors that we have in our midst. But once we are talking about types, remember we just talked about sources. Okay, but if we like to look at types of errors, basically we have two of it. That is the roundoff errors and the errors due to a truncation. So we could say that we have roundoff errors and truncation errors. These are the main two main types of errors that we have. So let's take a look at this one by one. So as we start from the sources of error, these errors, that is the roundoff, which is also known as machine error. That is the process of rounding off what computations and values and numbers. Okay, in effect, this type of errors could be termed as chopping. Okay, that is when we discard some number of decimal places from a certain point. Okay, we could also term it as that. And this also arises because digital computers and devices are not able to represent some quantities exactly. Okay, and this for you as engineers is very very important because once you are dealing with such systems, it's very good for you guys to know because it gives you a fair idea of what errors you are likely to make, and if you forgo of that, it can lead to erroneous results in your calculations. Okay, because once you start rounding off numbers before you get to your solution, you are making so much error at the end of the day. And because these errors are there, as I said earlier, if you don't really take care, they can lead to some of your systems going unstable, and technically we'll move on to some erroneous results. And with this, once we experience some this kind of situation, these are being termed to be health conditions. That is systems having so many errors in them. We term them to be health conditions. And one thing that makes this thing more serious is that they are very difficult to detect, and if you don't take care, you might not even see them. Okay, so that is why for any device that you are going to use, in their manual, they are going to really specify so that though you may not see it, but at the back of your mind, you should know that there is something which is not being accounted for, of which you need to have a fair idea of. Okay, so just as the value of pi, okay, when you are working out with this on your calculators, I think it's going to cut up to I don't know whether 6 or something this bunch and neglect of all of these decimal places. So once you start working in these areas, you know just exactly what is happening. So let's take an instance where we are using two different softwares or let's say devices. So I would like to estimate this expression as we have it here. And because of the level of precision of devices or softwares, I'm going to use two softwares here. That is Microsoft Windows. It comes with a calculator, and I'm also going to use Excel, all to perform this same computation. Okay. And once I did that with the calculator from Windows, this is the value that I'm getting. Okay. I did same with Excel, and this is what Excel is giving me. Okay. Now, because they all have different way of expressing this value that we have here, okay, that is the same as this pi. They have various ways of expressing their level of precision in terms of pi. Let's look at what is happening. You can see that this is giving us minus 206.76, and Excel is giving a negative negative 206.94. Right from here, you can see the level of error that we are going to account here, because these two software, that is the Microsoft app and that of the Excel, have different way of representing precision in terms of what pi. Okay, so all of these are some of the roundoff errors we can come up with. Okay, yeah, so let's see how these systems get to round off, and as a result come up with this sort of what errors. So the first way to be is to run down, and I believe we know how to run down and round up numbers. Okay, so for instance, if we would like to round up 8.43 to one decimal place, because we are running down to one decimal place, means that we are going to focus on this 4, and because the next value happens to be less than 5, it means that we are going to run down to 8.4. So in this case, this decimal place, that is the fourth one, is not going to increase. Okay, similar thing is being seen here when we like to round off this number 6.281 to 2 decimal places, and because this 2 decimal places, the next one is not bigger than 5, we just have to maintain the 28. In that same case, if you should have numbers, like for instance, we are rounding off this same 8.4, this time 8 to 1 decimal place, because this 8 happens to be greater than, let's say, 4, it means that we are going to round up to that number, and same thing can be said for what this expression that we have here, to 2 decimal places, and we have that to be 2.28. Okay, so we are going to run down or run up based on the decimal place that we are interested in. So basically, that is how round off errors are being seen, and because we are just running off numbers and running off numbers, we are bound to estimate or incur some error in there. Now let's look at the other side, opposite side of the error, which is truncation error. Now with this truncation error, this error comes as a result of the fact that finite or infinite sequences of computational steps necessary to produce an exact result are being truncated prematurely, as we discussed in the sources of errors. Okay, so with this, suppose that we have an expression, should I say either the Maclaurin series, which is a special form of the Taylor series, or any of these two series, and we like to estimate for a certain value, and we truncate it at a certain point. Okay, just as we saw in our previous example when we were truncating from term to term, just think or just see or witness the errors that we occurred in there. All right, so once we have an expression and we truncate them that way, it means that definitely errors will come in. Okay, in that same case, let's think of our problem that we started with the chapter 1, that is the jumper. Okay, in that same case, if we were to truncate in a way that expression in there, we are going to lose some sort of information in there. So that is also another part that we should have looked at. So let's take a look at this Taylor series, how we get to come out of that. So with this, we are going to make use of this a special form of this Taylor series, which is also called the Maclaurin series. But remember that before you can get the Taylor series, that is just we make x is equal to 0 in the Maclaurin series, and that is going to help us achieve the Taylor series as we have in here. So this expression that we have down here gives us the Taylor series, of which we are going to need in coming up with what we call the numerical differentiation. It will be a very important thing to you as we move forward. Okay, so this problem that we had right from the beginning could also be expressed in the form of Taylor series. That is the jumping problem. So if you look at this is being expressed in terms of f, the function f. But however, we can translate that same idea to our jumping problem where we are trying to estimate the velocities. So instead of f, we are using velocities here. Okay, you could also just change it to f if you like to, if that will be simpler for you. Okay, so in this case, this is what we have. That is our velocity at time ti plus 1 will be equal to velocity at ti, then the remaining continuums and that. Okay, so if you look at this critically, this is just like having, let me just place this side by side and let's see what is happening here. Side by side, we have that. Okay, so this is just like let me just get this. Yeah, exactly as we have here. So if I should copy this and place it here for the meantime. Okay, just here like that. Okay, yeah. So if you look at this carefully, now this, our fx plus h is the one that we see here. Okay, and remember that ti plus 1 is the same as the time ahead. Okay, and that is the same thing that we've expressed down here, x plus h. Now this h that you see here is referring to the step size. So if our current value is here plus our step size, that is definitely our next value. Okay, so that has been represented by ti plus 1 here. In that same case, we have f of x, which is the same as the vti. Then we have f prime of xh, and we have v prime t of xh, and remember h here is the same as the step size. Okay, so this is just a replica of whatever we have in the Taylor series. Okay, so going back to our slide, which is that, yeah, so that is what we have in here. So that is how we modified our velocity problem to that of the Taylor series. Okay, now let's see something here. Because we cannot write all of these terms, it means that we will definitely have to find the summated version of the remaining, which is being represented by Rn here. This Rn that we see is just a summation referring to all the terms that we may not see. That will be more or less like the end term of this whole series, of which we cannot easily come up with. So this expression that we see here would represent the terms that we do not include. Now with this, let's try to truncate up to a certain point. Okay, now in truncating, let's truncate to the first derivative. Okay, and in truncating to the first derivative, we truncate everything right after this part. Okay, and express everything in here as Rn, more or less like the residuals. Okay, so once we do that, we come up with this, and making this we bring this back here, trying to make our VTI the subject, that is this one, we come back down to this expression that we have here. Now with this, let's look at what is happening. Because we made V prime the subject, V prime of Ti, it means that everything that we have here will come to this side, okay? First of all, this VTI will go here. All over, we divide everything by in here, and that is why we have the Ti minus Ti, okay? Plus, don't forget this thing that we have in here, okay? And that is also that. But watch it. Once this R1 moves, this becomes negative, okay? Sorry about the typing. I think the same thing. Yeah, so the one in the lecture material happens to be correct. So once this R1 moves here, this becomes negative, okay? This R becomes negative, so this will become negative, okay? Now, in reality, once we do the approximation, this will be the term that we are going to use, okay? Minus the residuals all over the RT, because we divide everything by Ti plus 1 minus Ti. That is why this is also happening that. Now, because this is the approximation term, whatever is being left will be the truncation error, okay? Because once we perform our approximation, and because that is not exactly the true value, okay, the remaining of what we get, it will be our truncation error, okay? And we can use this term in here to come up with so many things, such as the numerical approximation and the differentiations, okay, which we are going to look at very soon, okay? So all these things that we are trying to do here is just may seem blur for now, but once we start with the chapter 3, where we are going to perform the actual numbering, manipulating numbers and stuff, this we see really the relevance of that, okay? Yeah. So once we have this expression that we see here has a formal name or a formal label in numerical method, which refers to what? The first order finite differencing, okay? Now, with this finite differencing, we have it basically in about 3 ways, but this will be the general formula. So this general formula, just as we have in here, we are just changing everything back to f's instead of what? The velocities. So in this case, we have our f prime of x, which is the same as we have in here. We have our f of xi plus 1 minus f of that, which we have up here. And the same, the change in t, which we have as change in x, we have down in here. And this last part that we have here has been expressed as what we have in here, okay? And this is from the expression that we have here. It's just a way of what? Summarizing everything that we had in here to this O and changing t, okay? So that is what we have in here. So with this, our expression now changes finally to this when we change everything that we have here to the step size, which is equal to h. We are just representing our step size by h, and doing the same thing to this side too. We are having this, and this is what we term to be the forward finite differencing. Now, the forward differencing, because in estimating this our xi, we are going to need values from the future, that is our future value, that is xi plus 1, and that of our present value. So if we are to stand on our present value, we will need a value from the future, which is the same as forward, okay? So that came as a result of the name. We are basing on values from now, that is the present value, and that of a future value, more or less like a forward value, okay? So that is why we have the forward differencing. So let's look at this pictorially. Now with this, we have, to us to estimate our true derivative, that is our f prime, we will need a certain current value, that is the xi, and a future value, which is the xi plus 1. and the difference between them is what we have as the step start, which is the what? The h. Okay. In that same case, we could multiply this function or equation such that we are going to need values from the past, which in this case we are going to stand on the present and that of the past value to come up with our derivative. And because we are moving back, we refer to that expression to be the backward differencing. Okay, so with this we are going to need a current value, unlike the forward approximation where we use the forward value. With this we are going to use the past value, that is xi minus 1. And once we do that, we get this expression as we have here. Okay, so all these are part of what? The truncation errors, of which we are going to look at very soon. Okay, we are going to look at very soon. So with this, it's going to need the current value and that of what? The past value. So the term backward differencing. Now, just as we are using the forward, the present value, and that was the past value or the future value, we can think of a way of combining these two as one. Okay, now once we combine these two value or these two approximation, we can get what we call the centered differencing. Now with this centered differencing, we are not going to need the present value, which is the xi. However, we are going to need the past and we are going to need the present value. Now, once we have this, we can find a way to combine all these two, and this could be done through subtracting the backwards differencing from the forward Taylor series expansion, as shown in here. So once we do that and we truncate at the first derivative, it yields what we call the centered differencing. Okay, and remember from this that because we are not dwelling on the present value here, which is the xi, our change, that is our step size, will be equal to what? 2 times the step size. Okay, and that is why we have our 2h here, unlike the other ones where we had h all over h. In our case, we are going to have 2 times of what? The step size. Okay, so with this we have it as a function of our future value minus a function of our past value, all plus the truncated error that we have in here. Okay, and if you look at the previous ones, it gives you an indication. You remember that for the backwards and the same as that of the forward, everything here will be as that of the what? OH. But in the case of the center differencing, this term here will be equal to what? H squared. Okay, this H squared, and this talks so many things about the error. Okay, so in the case of the forward and the backwards, it means that anytime that we have the step size, we are in a way halving, or let's say reducing the error to by half. But in the case of the center differencing, because of this notation that we have in here, which is mean squared, it means that any time that we have our step size, in effect, we are reducing our error by about say 4. Okay, so this is what basically this term really means, and we are going to demonstrate this really soon. Okay, so with this, we've been able to come up with 3 notations now. That is the forward, the backwards, and the center. Okay, now with the forward and backwards, they all have this term LH, OH, and also a step size as H and H. But in the case of the centered has only 2h, that is 2 times of the h, that is the step size, and also this h here is being squared. And remember, all these have their meanings. So in the case of the forward, once I have the step size, I'm also reducing the error by half. But in the case of the centered, as I reduce or I have the step size, I'm reducing the error by about 4 times. Okay, so let's see what is going into the forward approximation, that is the forward difference, final difference. For the forward difference, we need a current value, which is the xi, and a forward value, or let's say a future value, before we can estimate it. Now, in the case of the backward differentiation, we need the current value or a present value as xi and a past value or a backwards value as we have in here. That is the xi minus 1. In the case of the centered, we need a future value, that is the xi plus 1, and a past value. Okay, so once we have this, we can estimate for the first derivative of any expression. Okay, so we could see all that. Now, because halving the step size will reduce our error by half, I mean in terms of the forward and the backwards. However, in the case of the centered, halving the step size will reduce the error to about 4 times, makes the central difference much more accurate than the forward and the backward difference. So just as some of you in future will be coming up with algorithms based on some numerical approximation and stuff, and you are being faced with a challenge of selecting any of these numerical differentiation techniques, I would suggest that you go in for the central differencing scheme, because with that, anytime you have your step size, you are in effort reducing your error to about 4 times. Okay, and that makes it very, very efficient whenever you implement this in your algorithm. Okay, so with this, let's try to demonstrate really what we are trying to achieve in here. Okay, with this numerical differentiation schemes. Okay, now remember that before we can get our forward, we need forward differentiation approximation. We need a current value, that is the current value, and a forward value. So in fact, we need a current value, that is the xi, and we also need a past value, current feature value, that is xi plus 1. Now in the case of the backwards, we need only a current value and a certain past value. Okay, so we have a current value here, and we also have a past value, that is xi minus 1. Okay, now let's look at the center. For the center, we need only a future value and a past value, okay, of which we have a present value here and a past value here. So it means that for any of these schemes, once we have these three, let's say, estimates, we can estimate whether it being the forward, the backward, or the center. Okay, now let's see how that happens. Suppose that you are being asked to estimate the forward backward differences scheme as well as the center differencing approximation to estimate the first derivative of this function that we have here. Okay, so this is the function that we have, and we've been asked to find the first derivative of this function based on the forward, backwards, and center differencing scheme. Let's see how we can achieve that. Okay, now for us to be able to do this, we first of all need to know our present value. Now with our present value, that is the one which has been given as x, which is equal to 0.5. Okay, so it's more or less like a number line, and we have our current value to be 0.5. Okay, as we have in here. Okay, now remember from earlier that before we can solve for any of these approximations, we need our current value, which has been given to us. We also need our forward value, which we are yet to estimate, and also our past value, which we are yet to estimate. Okay, so we have our present value, our current value at 0.5, and before we can get our past value, which is the one that we have to estimate here, all that we need is the step size. And remember, from the present to the past value, the difference between them is the h, which we have to be equal to what? 0.5 in here. Okay, so once we subtract 0.5 from our current value of 0.5, we are having what? 0. And this 0 will be our past value. In that same case, if we like to estimate our future value, whose difference is also h, our future value will be equal to our x, which is equal to 0.5, plus our h, which is also equal to 0.5. And once we do that, we are getting our future value to be equal to 1. Okay. Now, let's look at how we get to estimate for the first derivative itself. However, before we get there, let's see if we can get the true solution. Okay. And before we can do that, you know that we are trying to estimate for the first derivative. And this is not a complex function that we cannot solve. That is, if we try to what? Differentiate this. And once we differentiate this, we are getting this equation that we have. Okay. But as always, once it comes to engineering, there are some equations that we cannot easily differentiate. That is why we go through numerical. Okay. But for this one, it's easy, something easy that we can do. So let's just try that and see. So once we differentiate this function, we are getting this expression that we have here. Okay. And with this, we can, once we have the differentiated expression, we can just put in the value that we are looking for, which is x is equal to 0.5. So once we put in f prime of 0.5, it's just a matter of finding for the numerical value. Okay, that is, in this case, we are just going to place x is equal to 0.5 wherever we see x. And once we do that, that is going to land us as well, negative 0.9125. Okay, so because we went through calculus, this could be termed as what? The true value. Okay, but this is where we would like to bypass calculus. So let's see really how to do that when we use the numerical differentiation scheme. That is the forward, the backwards, as well as what? The differentiation scheme. So just as we did earlier, for us to get our current, past, and future value, all that we do is to subtract the step size, which is h, from the current value. And once we did that, we had 0 and our future value was equal to 1. Okay. So we just try to find a functional evaluation of these values. Okay. So f of, that is the past value, which is the same as the functional value of 0. And remember, this functional value is when we place 0 into our original function here. Remember, we are going through calculus, so we are not going to deal with this calculus differentiated thing again. We are going to base our solution on this original formula here. Okay, so once we put in f of 0, that is why, so everything here goes to 0 with the exception of what? This 1.2. So that is how come we are having 1.2. In that same case, we are going to find the functional evaluation of 0.5. And in this case, we are going to put 0.5 anywhere we see x in this expression. Okay. And once we do that, we are getting 0.925. Similarly, we do same for this last one, which will be f of what? 1.0. And in that same case, we put x is equal to 1 for every of these x's that we see, and doing so we get 0.2. Now let's see how we are going to compute our forward differentiation. Now remember that our forward differentiation scheme, the formula was giving us f of xi plus 1 minus f of xi all over h. And we know that f of xi plus 1 has been calculated here, which we have to be 0.2. So that is why we have 0.2 here. The next one is minus f of xi, and we have f of xi right here, which is equal to 0.925. 0.925, which is exactly as we have in here, all over our h, which is our step size, which we were given to be 0.5 as we have in here. So once we estimate this, we are getting negative 1.45. Okay, and with this comes with an error of 58.9. Okay, and this error is being based on the true value. And remember how to estimate our error based on the true value. That is when we have ET, which is equal to the true value minus the approximated, all on the true value, all times 100. Okay, so don't forget that. So this was how we calculated our error. Okay, that is why we are getting the 58. Okay, so that is for the forward differencing. Now let's try to look at the backwards differencing. Remember that for the backwards differencing, the formula was given as f of xi minus f of xi minus 1. Okay, now we already know our f of xi to be equal to negative 0.925, which we have here, minus f of xi minus 1, which we have to 1.2. So that is our 1.2, okay, all over our h, and we are getting negative 0.55. And with that also, we are getting an error of 39.7%. Now finally, let's look at that of our centered differencing. And the centered differencing, the formula 2 was given by this, okay, and that is xi plus 1 minus f of xi minus 1. Okay, and already we know the f of xi to be that, and f of xi minus 1 to be that, and that has been placed right in here, all over 2 times of our step size. Okay, and remember our step size was equal to 0.5, so 2 times of 0.5, and that is giving us 1. Okay, as we have in here. So once we simplify, we are getting negative 1.0, and once we estimate the error, we are getting 9.68%. Okay, now if you look at these 3 schemes, forward differencing is giving us 58.9, backwards is giving us 39.7, and that of centered is giving us 9.6. So just with the look of these errors, you can really say and see that the centered differencing scheme is giving us something much more smaller than that of what? The forward and the backwards. Okay, so that is why at the beginning I was trying to say that the centered differencing is in a way known to be very accurate than the forward and the backwards. Okay, just based on that. Okay, also we did made an assertion that once you have the step size, the error is being reduced by half in the case of the forward and the backwards differencing. However, when you have this same step size in the case of the backwards, you are going to reduce the error to about 4 times. Okay, so let's try to also demonstrate that. So because we are having our step size this time, it means that our h will be reduced to from the 0.5 to 0.25 because we are having our step size. And let's see the outcome of this. Okay, let's see the outcome of that. So with this same thing, because we are having our step size, it means that with our current value of 0.5, for us to get our past value is going to be 0.5 plus our step size, which is now 0.25, which we are going to get 0.25. Okay, so it's going to be 0.5 minus 0.25, and that is going to give us our backwards value, which we have to be 0.25. Now for our future value or our forward value, which will also be 0.5 plus our step size, which is going to 0.25, this gives us 0.75 as we have right here. Okay, so in calculating for the functional evaluation, that is where we place this into this formula. Okay, this expression, we are getting these to be equal to 1.103 something something. For him, it maintains the same since the present value did not change. And for that of the future value, the functional evaluation is now equal to that. Okay, so let's try to estimate our forward, backward, and center difference again. And once we do that with our forward, just going through the same as we had earlier, this is giving us an error of 26.5%. Okay, and remember from earlier we had 58.9. So this new value is more or less like half of the 58 that we had, which came as a result of halving or reducing the step size by half. Okay, so this confirms the assertion that once we reduce the step size by 2 or half it, we are going to reduce the error through by half. Okay, now let's take a look at the backwards differentiation, and now we are getting 21.7%. And earlier, remember that we had 39.7%, and we are now getting somewhere 21, which is approximately getting to half of it. Okay, and finally, let's look at the center differentiation, of which we are getting 2.4%. And from earlier, we had an error of 9.6. So you could see that once we have the step size, in a way, we are reducing the error about 4 times once it comes to the centered differencing. Okay, so it will be more prudent to use the centered differencing if you would like to come up with your own algorithm one day, sometime in future. Okay, so that makes it's just a demonstration of how these numerical differentiation systems work. Okay, it's being used to estimate the differential of functions. However, when it gets to certain cases where the differential can be very difficult to estimate or come up with, we make use of the numerical differentiation schemes, and that is going to help us really get that. Okay, so that is that. So with all this said and done, what happens when we combine our truncation error with that of our Roundoff error? And this gives us what we call the total numeric error. So in effect, this total numeric error is equal to the summation of the Roundoff error plus that of the truncation error. And that is going to give us this total numeric error. Okay, so with this, let's see how to minimize this error. Now, observing critically from Roundoff, or even from your own perspective and from what you've seen, even just by using softwares and systems, your smartphones in analyzing or computing certain things, you can agree with me that one way of minimizing Roundoff errors is to increase the number of significant figures or the number of decimal places whenever you are performing any computation. So just as in the case of pi, when you are trying to perform computations with it, make sure that you use a very high number of decimal places if you would like to reduce Roundoff error, okay, and that. But this same Roundoff error is also likely to increase when you perform so many iterations, in the sense that when right from the beginning you start rounding off and you perform more iterations as you move on, you'll be accumulating so much Roundoff error in your system, in your analysis, and that is also bound to increase. Okay, now let's look at the other side of truncation error. Now, this truncation error can also be reduced when you decrease the step size, in the sense that once you decrease the step size, this in a way is going to going to reduce this error to a certain point, which we are going to look at it graphically very soon. Okay, so once you decrease the step size, which can look to an increase in computation, which in the case is the increased roundoff error, it means that in your attempt to decrease the step size and decrease the truncation error, you are in a way increasing roundoff error on the other hand. So we are going to be faced with a challenge of coming up with a strategy of decreasing the other whilst maintaining the other. Okay, and that is some sort of a very difficult challenge that we as engineers experience all the time. So more or less, like, as we are attempting to decrease truncation error, we are increasing roundoff error on the other hand, and that becomes also another problem. So let's look at this plot as or graph as we see in here. So we have our error going up and we have our step size this way. So okay, so as we increase our step size, we are in a way decreasing our roundoff error. Okay, because if we are using a bigger step size, it means that our iterations will be less. Okay, in that case, we'll decrease our roundoff error. However, if we increase our step size, it's also increasing our truncation error. Okay, so in attempt to reduce one, also increases the other. So what do? What we try to do is to find a point of diminishing returns where the effect of the other one would balance out the other. Okay, and with this, we may not be able to do it with our physical eye, and it's sometimes very difficult to do. So softwares like MATLAB have some way of dealing with cases like this when they try to increase the number of tickets to about 15 or 16 floating points. That is what softwares that I've tried to come up with. Okay, so that is something that as engineers we need to find a balance between. Okay, so software such as MATLAB and the others are very potent, or in a way have find a way to minimize this effect to a certain level. But let's hope in future we could find a way to do away with all this. Okay, so with all this, let's see how we can control errors, because for errors, whatever happens, we're always going to see them and they're always going to come up. Okay, so in effect, there is no precise way of evaluating numerical errors for all problems. Okay, in many cases, these errors or estimates are being based on experience and judgments from you as the engineer or the scientist, and that is something you guys would have to we are going to really experience once you get to the field. So for as engineers, we always try to settle for some sort of estimate of the error in our calculations, and let's see how we get to do that. And as engineers, you should always be prepared to perform numerical experiment to increase your awareness of computational errors. Okay, so for us to really deal with it, these are some of the things that we usually do. We try to repeat our computation in so many different steps with so many different step size and methods, and compare the results. The one that we think gives us something really small, we use that to be our optimal one. Also, you can also choose to employ sensitivity analysis, where we change the solution, whereby we try to adjust some of the parameters and see the changes that happens on our final results. Also, we could also think of trying different numerical algorithms and that have different theoretical foundations, which we are going to look at in chapter 3 very soon. And also, we also look at numerical computations, which are extremely critical and may involve loss of human life. For this kind of system, you have to perform so many independent groups of experiments to compare the results, so that we try to in a way minimize the loss of casualties to a very minimum level. Okay, so these are some of ways in which we could control our errors that we see, or errors that we shall encounter in the course of our duties. So basically this will bring us to the end of this errors, and we've talked so much about errors, starting right from accuracy to precision. We've taken a look at sources of numerical errors and the two types of the errors, that is the roundoff error and the truncation error. And this roundoff error comes as a result of trying to round off numerical, let's say, values and all that. And it came down to the truncation, and that has got to do with expressions, mathematical expressions, whereby we terminate them prematurely, and this also leads to that. So we also demonstrated in the case of the Maclaurin series to determine that as we add extra terms, our error is being reduced to a significant level. Also, we saw that of the Taylor series, and we demonstrated how the final differences scheme is. We got to see that the center differences scheme provides much more accurate results than the forward and the backwards. And we demonstrated that also having the step size reduces the error by half in the case of the forward and the center. However, in the case of the center differencing, it reduces the error by about 4 times, making it more potent than the other two schemes. We finally came down to total numeric error, that is the summation of the roundoff error and that of the truncation error. We got to see that as we increase the number of decimal places, we get to reduce the roundoff error. In the same case, as we increase the number of iterations, that affects the roundoff error highly. That is, it increases it, but in a way, it decreases the truncation error. So in our attempt to decrease one side of the error, we end up increasing the other part of the error. So there's always the need for us to find a balance between these two errors. And finally, we talked about how to control some of these numerical errors by trying different schemes, by going up with performing sensitivity analysis, changing, adjusting some of the parameters to see its effect on the final result and selecting the best one. Okay, so this is basically the gist of errors. And now that we are done with errors, our next section will be to look at numerical solutions to nonlinear equations. And ladies and gentlemen, this is where the mathematics will start from. So now we have a fair idea of what numerical approximations are. And whenever we are doing that, how we get to estimate the error. So with these two ideas and knowledge now, we can really take problems, nonlinear equations, and really solve them. And this is where the mathematics really start from. Okay, so I'll see you guys in class, and if you happen to have any problem, okay, you could drop it down in the VLE, or better still, when we meet in class, we can discuss this together. So on this note, I'm going to end here, and we are going to continue this lecture in class. Bye bye for now.